Hey, so the question came up about oxidation reduction reactions. So if we just need to identify if something is an oxidation reduction and we're not trying to just figure out everything in it, there's a rule of thumb you can use. It's not perfect. That's why it's called a rule of thumb. But single displacement, combustion, synthesis, and decomposition usually are going to end up being oxidation reduction reactions. The one that is not is going to be double displacements. It has to do with double displacements. Their charges don't change at any point in the reaction, and so the oxidation states also end up not changing. So I'm going to show with some of these examples right here. So when you're doing oxidation reduction, if you follow the rules, one of the big rules is what I have highlighted over here. And it says that if you have a neutral single element or a diatomic, but it's just an element, it is 0 as the oxidation state. So for example, this oxygen right here, that guy is 0 oxidation state. This Hg is by himself, and so he has a 0 value oxidation state. I'm going to jump on down to this problem right here. The sodium again is by itself, so its value is 0. The hydrogen is diatomic. Notice it's 0. And I'm going to jump on down to the next one. Magnesium is by itself. Its value is 0. And then the hydrogen is diatomic. It's 0. That's the first thing that you want to make sure that you're understanding. The second thing is you want to pay attention to the total charge that something has. So if you look at the HGO right here, the whole thing is neutral. So the whole thing has to equal 0. Kind of like when it was alone, it was 0. So HGO, the whole thing has to equal 0. Now there's an order you're supposed to do these elements in, and if you'd watch the videos on this, you can see that there's an order to it. Nitrogen, I meant to say oxygen is really high up in the order of what gets their charge first. And generally speaking, on the periodic chart, like if you need a nice visual, so here's our chart. So these guys, their oxidation state is 1, which also is their charge. I know it seems like the same, but it's not. They get theirs, like if they're combined with something else, they get preference. So if we go right here, here's our fluorine, and he's the second guy to get his oxidation state. Like if he's in a compound and no one else is in the compound, then his oxidation state is -1. And if anyone besides an alkali metal is in the compound with him, he gets his oxidation state as 1, and you have to figure out everyone else. And then the other ones that get priority is we have oxygen. So oxygen, his oxidation state is -2. It's easy to remember these few guys that are super important because their oxidation state is the same as their charge, even though they are not the same thing. So that would be third in order. And then the fourth in order would be this hydrogen over here being +1. That's the fourth in order that you do it. And then after this point, you're going to be basing it on the most electronegative element gets its oxidation state first. And if you're wondering, what is most electronegative? I know you don't know it yet, but it's this side of the chart right here. You're about to be learning about this, but this is electronegativity side right over there. So anything that's close to this side is going to be getting its oxidation state first. Now, that's if you don't have those other 4 guys I just mentioned on it. So what we're going to do, we're going to look at HGO. So this is this first one, HGO. And if we're looking, first we're starting, is there an alkali metal in it? This first option. No, there's not. Okay, what about fluorine? He comes second. Nope, there's no fluorine in there. Oxygen. Oh, oxygen's in there. So oxygen gets his oxidation state first. Since the whole thing is neutral, it has to add to 0. So what is mercury going to be? Sorry, those are speed boxes. Well, for it to work, mercury has to be +2. So that's how oxidation state stuff happens. So you'll notice up in this problem, mercury was +2, and then it was going to something that was alone, and its oxidation state was 0. So it's changing. So if you have a change, that means it's oxidation reduction. So I'm going to jump to the third problem. I'm going to do NaH. So for this guy, remember the first thing we check is this first column. Is there an alkali metal in there? And you should see, yes, there is. Sodium is the alkali metal. So he gets his oxidation state of +1. Don't know hydrogens, but we know the whole thing again has to add to 0 because look, this guy, the whole thing is neutral, so it has to be 0. So you can probably see that that should be -1. So when we look up here, you can see that 0 goes to -1. That's a change in oxidation. Whereas, and also the sodium, he's going to +1. Now on this third one, we're going to do HCl and MgCl2. So HCl, and then we're going to do MgCl2. So what we're going to say in here is we're going to say, all right, do we have an alkali metal in either of these? No, we don't. Okay, do we have a fluorine in either of these? No, we don't. Do we have an oxygen in either of these? No, we don't. Do we have a hydrogen? Hydrogen's the fourth one. I made him kind of look weird over there. Yes, we do, in one of them. So hydrogen is +1. I don't know chlorines, but the whole thing has to equal 0. Well, what +1 equals 0? -1. Yes, that is the same as its charge. It feels like we're doing a charge balance right now, but we aren't. We're doing oxidation states. Sometimes it works, sometimes it doesn't. You'll notice right here in the one we did before, the oxidation value was not the same as the charge of hydrogen, which is +1. So you got to kind of be careful how you're doing this. Now we've got MgCl2. So if we look at Mg, we already ruled out everything. It didn't even have hydrogen in it. Well, the fifth rule is that you're going with the most electronegative element, the one that's closest to this corner. And I'll tell you right now that chlorine is right there. And magnesium's like way over here. So chlorine is definitely closest. So we're going with him. And so in this box, each chlorine is -1. That's its charge. It's also its oxidation state. But there are 2 of them. And the whole thing is neutral. And we don't know what this one is. So if this is -2, this is -2, then we know that magnesium has to be +2 to equal 0. And that's why our magnesium right here is going from 0 to +2. See, there's a change going on. And also down here with our HCl, we can see that our hydrogen is changing. Now, this one will confuse people because they'll be like, well, there's something that isn't changing, right? So this guy isn't changing. So it can't be an oxidation state. Well, if anything is changing in the problem, aka the magnesium or the hydrogen, if anything is changing, then it's a redox. Some of the elements won't change. That's okay. Last thing we do right here is if we're going to do this last problem. Now, this is a double displacement, and I know that because I've got something positive and negative. And so I know that, but we're going to go ahead and do the oxidation states for the practice really quick. So KCl, here's all of our compounds, AgNO3, AgCl, and KNO3. All right, so first, do we have anything that's an alkali metal? Yes, we do. Potassium is an alkali metal. He automatically gets +1. Now, do we have anything else? Okay, so alkali metal, the next thing, do we have any fluorines? No fluorines. Do we have any oxygens? We do have oxygens. So each of these oxygens, the whole thing is going to add to 0, but each of those oxygens is -2. So -2 times 3, -2 times 3. It's just times 3, not times the charge. The whole thing has to equal 0. And we're adding him, plus him, plus him. And we're adding him, plus him, plus him. Now this one's kind of easy to see. Right now what I have is I have a +1 plus X. I don't know nitrogens. I could call it nitrogen. Minus 6 equals 0. So nitrogen is equal to 6 minus 1. Nitrogen is equal to 5. So that's +5. Now if I go over to the Cl, that one was really easy because it's this plus this equals 0. So he's got to be -1. And if I go down to this AgCl, I am going back up to that AgNO3 in a second. So AgCl had gone through everything, and so it's only the 5th rule that applies, the most electronegative element. So chlorine is over here, and Ag is like in this section, a little further down, but down there. So chlorine gets his -1. Don't know Ag's, but has to be neutral. So you could probably see that that's +1. Now, the easier way to do something like this, so Ag and NO are kind of unknown. They're in that list of like electronegative and what are you going to do? Okay, so in this case, we already have one guy labeled. The best way to handle this is to break it into the little group. And I have how to do this up here with the NO3. So I'm going to come up here, how to do NO3. So again, we know that they are going to add up to -1. And so our question mark is the nitrogen, and we have 3 oxygens times -2. The whole thing equals -1. So nitrogen is equal to 1 plus 6 is plus 5. So I've got that equaling to plus 5. It's easier, much easier to do these like this. All right, so I've got that he's plus 5. Now I can say that Ag plus 5 minus 6 is equal to 0. So Ag is equal to 6 minus 5, which is equal to plus 1. By the way, Ag is usually plus 1 with these things, or 0 if it's by itself. And you go and you look at all of these in. I've got them all filled in. And here you will see that none of them change. The Ag on both sides is plus 1 and plus 1. The Cl is -1, -1. The K is plus 1 and plus 1. The nitrogen is plus 5 and plus 5. And the oxygen is -2, -2. So nothing changed. That's why this is not an oxidation reduction problem. Feel free to ask me more questions on this. Just wanted to kind of do a review. I know I spoke very quickly. So again, feel free to ask questions.